This conference will now be recorded.
Okay. Okay, this is what we are going to talk about, prototype test, device design, and progress update. And three of us have been working on this for a while. Okay, let me give you I updated my bio to put in that I have invented a new class of solutions called asymmetric information resolution. And I've done that for strategy and for financial analysis. I'm sort of 70% completed on competitive analysis. And also, I recognize that collated distributions do exist, and it's going to be a very powerful tool if we expect the financial services to give us some good information. That's the way to do it. And down here, I discovered the massless formula for gravitational acceleration in 2007, and it's valid for all macro forces, electromagnetic, mechanical, and gravity, which quantum theory has not been able to do. And also, I proved that the gravitational constant is not a constant, it's a coefficient that's a function of the isotopic mass of the element, and that is the value of K isotope. So when you multiply, when you divide this constant by the isotopic mass of the element, then you get the gravitational coefficient. The reason why I say the universe's expansion is not due to dark matter is because as nucleosynthesis occurs, the isotopic mass of the elements increases, and therefore the gravitational coefficient decreases, and the forces are not so great. The universe starts expanding. The other thing I've done is I found a replacement for the Schrödinger wave function. I call it the probabilistic wave function, and it's actually more than 100 years old. It was the original wave function that was used by physicists about 100 years ago. And I found it and tested it against a lot of things, and it works perfectly. But that fact has upset a lot of theoretical physicists, so I don't talk much about that. But it becomes key to understanding probability and randomness, because my interest is, after gravity modification, my interest is in interstellar propulsion. And we cannot do interstellar propulsion by going to higher and higher velocities, because Lorentz-FitzGerald transformation prevents us from reaching the speed of light, because everything goes to infinity. So the only way to bypass the Lorentz-FitzGerald transformation and the gravitational Newtonian transformation is to use probabilities. Okay, Mike Doty will be talking after I give this introduction. I think this introduction will probably take about 20 minutes, because most of you have heard this. It's a refresher. And then Mike Doty will talk about his design for a prototype test device. He has a mechanical engineering background, and his expertise is in manufacturing, analysis, design, testing, and systems integration. And he's worked in many, many industries: automotive, chemical, nuclear, medical instruments. I put this to one side. I cannot see my slides. Okay. Aerospace, and consumer products. Mike. And John Sokol is, he's the third member of the group that's been working on figuring out how to put together a test device, because I'm a lousy engineer. He's an information theorist working in robotics. He invented video streaming, ported BSD Unix to the PC, and 386 BSD became Free BSD, NetBSD, and OS X. He's also a major contributor to Linux, and this is his website. Okay, so let's start. Let's refresh on some fundamentals. What is gravity modification? To change your location requires two properties: vectoring, which is which direction do you want to go, and modulation, how quickly do you want to go there. It's the same whether if you have a interstellar propulsion engine that uses probabilities, it's the same two concept. Which direction do you want to go, and how quickly do you want to get there? So gravity modification is either or both of the local field. And why can't general relativity deliver gravity modification? Well, GR only describes the field. It assumes that the mass is the source, and nobody, not a single theory, has a source that's different from mass. So that's why none of the current theories can give you gravity modification. What we need for gravity modification is we need to change the mass source. And that's what we are trying to do here. Okay, gravity is a non-inertial field. If you have a region where velocities are changing, real or virtual velocities are changing, then the gradient of that velocity space is governed by this equation, G is equal to tau c squared. I'll get to it in a minute. And all macro forces exhibit this Nye field, and that Nye field is governed by G is equal to tau c squared. Okay. Now, if we look at the definition of tau, see in linear motion, the transformation is Lorentz-FitzGerald transformation. I call it lift for short, and it's governed by this equation that comes out of special theory of relativity. But a lot of people, we credit Einstein for discovering this equation. No, he did not discover it. He basically gave it as a reason why it exists and why the equation is of that form. But it was known many years before him that this equation existed, and that's how Lorentz and FitzGerald. Lorentz was a Dutch, and FitzGerald was Irish physicist. They knew about this equation. So this equation is much older than Einstein or special theory of relativity. Then if you look up the textbooks, you'll find an equivalent, which has never been given a name. So I gave it a name, Newtonian gravitational transformation. Basically, if you have a spatial gradient of velocities, one velocity is up here and higher velocity is down here, the horizontal, for example, and that's a difference in height. Then tau is given by the change in the transformations divided by that height, or the change in the Newtonian gravitational transformation divided by the height. And that's very simple. That's it. So if you're looking at so basically you're looking at the transformation here and the transformation here, find the difference in the transformation divided by that height times by c squared, you get your gravitational acceleration. And it's true for other macro forces, and I'll get to that in a second. So the surprise was that the linear Lorentz-FitzGerald transformation is equivalent to the nonlinear gravitational Newtonian gravitational transformation. And so if you plug in the mass, this is the mass of the planets and the sun, the radius, you plug in this is a calculated accelerations on the surface. You get an escape velocity. You convert that to time dilation and use Lorentz-FitzGerald transformation, and you get the equivalent velocity, and these two are identical. The errors are to the 10 to the power minus 4, 10 to the power minus 7, which is trivial. So there's an underlying consistency in how space-time works, and it eventually, in some of my later papers, I show that space-time is the carrier of force, not particles. And the reason why particles can be used to as a carrier of force is because all particles have to reflect the transformations present in their local space-time. So in effect, you're using particles as a proxy to what's happening in space-time. And that's why quantum theory has been able to explain certain things.
Yeah, that's a good observation. It's a result, not the cause, right?
Yes. The cause is actually space-time. And when you look at, in one of my later papers, I explain you have to have energy, conservation of energy is a very, very exacting requirement by space-time. And if you look at some of the theories, they find that they start breaking conservation of energy to explore the mathematics further. That is basically mathematical conjecture. Okay, universal description of forces. Here, when you look at gravity, acceleration g is orthogonal to the spatial gradient. If you look at the gradient here, you have the orbital velocities v1, v2, v3 as you get closer, and v3 is greater than v2, v2 is greater than v1. This is the naive field spatial gradient of real or latent velocity. So gravity exhibits a naive field, and acceleration is is orthogonal to the. It's basically the gradient of the spatial. It's a spatial gradient of velocities. Okay, and then if you look at electromagnetism, it also exhibits naive fields. You have the electric field here of electron moving in a magnetic field going into the page, and you can show that the naive field method also works. I think I have another slide here. This is the better. So you have the naive field plane here, and you have the electric field coming into the for electrons coming into the electron, and you have B, the magnetic field strength. With that, you have electromagnetic velocity, which is V. So you have a combination of the electromagnetic velocity, that gradient, this gradient here, then forms is governed by G is equal to tau c squared. Okay, so it's very straightforward. Same with mechanical motion. They also exhibits naive fields. If you have a ball and a string and you start swirling, you'll find that there's a variation in velocities. It's velocity, the tangential velocity is greatest here, and it's the least here. And that forms a spatial gradient of velocities, which again is governed by G is equal to tau c squared. So all these models, most people can, not most people, if you have the skills in modeling, you can build it yourself. So that's why earlier on, before we started the recording, early in the recording, I talked about specializing in context structure. You have to understand the structure of the context in which a phenomena is operating in, and only then can you model it correctly. So implications basically says that quantum theory is going to go away one of these days, and that all string theories are wrong, because strings are modeled by a particle expanding, the strings expanding with energy, whereas both Lorentz-FitzGerald transformation and the Newtonian gravitational transformations shows that particles contract. With linear motion, Lorentz-FitzGerald's contraction is symmetrical and identical to both sides of the particle. With Newtonian gravitational acceleration transformation, the far side is not as much contracted as the near side of the particle. So the particle looks like a lopsided what's the term? Ovoid. I think the name is ovoid. So it's sort of an egg shape, but it's sort of a flattened egg shape. And that causes the center of mass of the particle to shift towards the gravitational source, and so you see that as acceleration. Electrogravitics. Well, I talked to a Boeing senior manager some years ago, I think maybe 5-10 years ago, and I described to him what I was doing, and he said, "Oh, that's electric propulsion." I said, "No." That's why in some of my presentations, I say you have to know what you see and not see what you know. I completely went over this guy's head, what I was saying. And so I do this slowly so that everybody can understand everything I'm saying. So the reason why I put this in here is because people tend to mistake Nye fields with electrogravitics. I built a model. If you plot the electric field required versus the acceleration versus the electric field required, you can see by the decimal places, the effect is nominal to the electric field. And so the question is, where is the power delivery for this device that we are building coming from? And if you look at the spin, the rotation of the spin of the disk on which the magnets sit, it peaks up here at about 1100 RPMs, and then it drops back to 0. That's because the Lorentz-FitzGerald transformation, 1 minus v squared over c, the v plus the velocity of the plus the electromagnetic velocity, they start canceling out, and you get it peaks up here, and then as it starts canceling out, it comes out here, it comes down to 0. So the effect is about 1100 RPMs. So Nye fields are not electrogravitics. Electrogravitics requires that force is a function of the voltage of the electric field, whereas Nye fields require that force is a function of the velocity spatial gradient. Okay. So Mike, if you're ready, you can take over. Mike will talk about his design, which we had the latest update this morning. Mike?
Okay. Yeah, I can start it here.
Yeah, you should be able to.
We'll do the screen share. And
Okay, great.
okay, so this is the gravity modification experiment that Solomon has been discussing and presenting. So it's the version I have in mind for it, a kind of a simple, low-cost test for it. This is what you basically just saw in his presentation, a schematic version of what we're trying to do. And in this, so he has bar magnets on the bottom that have the magnetic fields going sideways. And this idea was to have them on a steel disc to keep the magnetic field to the one side up here in where the electric field. And then we have an electric field applied across the plates so that there's a conductive plate on the top. And in this case, one on the bottom. And in this case, the magnet disc itself would have the electric field. But that would require a commutator, basically a slip ring, to deliver voltage to the bottom plate. So another version is we have two field plates, one right above the magnet and the other one higher up. So you have this field zone like a pair of plates on a parallel plate capacitor. So we'll start. It's we're using, instead of the bar magnets, is to use a Halbach array, and that gives you more magnetic gradient on the top, as you can see, than the bottom. So it concentrates the magnetic field to one side, and that's in order to get a larger gradient. Solomon thinks that the bar magnets by themselves won't have enough of a magnetic gradient, and for the effect we're trying to create, it's based on the gradient and not just the field strength. Now you'll notice they don't really show the field direction in this illustration, but it has these kind of lobes on the ends which go in one direction based on these arrows on the ends. And then in the center, we have another magnetic field that goes in the opposite direction. So the center goes from right to left, and on the ends, it's going from left to right. So, and the illustration is somewhat misleading because these lines make it look as if the ends have the same field strength as the middle. But if you look at the shaded colored areas, that's the actual calculations of the field strength from this field simulator. Another option, you see, this is a 5-element Halbach array, and it's possible if we go to a 3-element, we could get rid of these end lobes entirely and just have a single direction on the field. But the problem with that is you won't see as much concentration of the magnetic field to the top instead of the bottom. Because as you can see on the ends, that you're seeing more of the field leak around the ends and go to the bottom. So, and on the bottom here, it's showing if you were to just have a regular magnet array of alternating polarity on the magnets, with none of them going sideways, you'll see you have a symmetrical field top and bottom, which is not what we want. We want it to go sideways and we also want it to be concentrated to one side of the magnet array. And the reason for that is that we don't want to see any effect of the magnetic field underneath the magnets, but only through the top, where it projects into the electric field between the plates. So in this experiment, we have this Halbach array layout. These are the magnets. These are these 1/4-inch cube magnets that are available commercially online. And we stacked them in this kind of an arrangement as shown in the previous picture. And we can fit 6 of these into a 4-inch disc. And this image here shows that if we have a retainer plate with slots that hold the magnets together, and that's because these magnets, in this kind of an arrangement, they have to be held together. Otherwise they'll want to fly apart. So they have to be inserted into slots or somehow held down. So we're using a laser cut disc to hold the magnets.
Question for you. What did you use to determine the polarity and direction of the magnets?
That previous diagram showing that shows a standard array that's even manufactured by K&M Magnetics, that's available.
Do they come pre-labeled for north, south, and the various directions?
No, they don't. But so you can tell which poles are which, compare them to other magnets. They do have magnets that are painted so that you know which end is north and which end is south. So, but in these cases, as far as I know, I don't think they're labeled. So. And then, so this rotating disc, it's mounted onto an assembly. This is a drone motor. And for those of you who are familiar with drone motor ratings, this is a 1,000 kV motor, meaning it runs at 1,000 RPM per volt of power, and it can go up to like 12 volts. So we can, and then this is run with a motor controller that adjusts the duty cycle of power to decide what your motor speed will be. So you run it at a specified voltage, and then the power delivered to the motor is determined by pulsing it on and off. Instead of using a voltage control, it's a duty cycle motor controller. And here's showing how it's arranged below the field plates. So we're using typical FRP circuit board material. It's copper clad to form the upper and lower conductive plates. So we can just connect it with a pair of lugs to the outside, and then the magnet spins below. And I don't have it shown here, but there's another plate on top of the magnets to hold them in place. And here, this is a cutaway view of the entire experiment design. So here you see there's the drone motor, the bottom base plate, and the retaining plate with the magnets in it, and then a top cover plate, and then these 2 pink areas are the field plates. Then there's a PVC pipe, 4-inch pipe that goes around the whole thing, so that to help contain it in case it flies apart. And then around the corner posts, then there's a set of stainless steel screws and washers with brass nuts that hold it together. So on the bottom, I have this circular plate that acts as a spacer to keep the PVC pipe centered to the motor. And then on the top, the other material that's cut, so they're all cut out of the same square of material, this base plate and this top plate that holds the upper piece of PVC pipe centered as well. So in this area here, this is your basically a big parallel plate capacitor, very low capacitance, but high voltage, where we're testing for the magnetic and electric field interactions. And here it's a rendering that shows it with the bottom PVC pipe removed, so you see the motor and assembly. And this is the complete assembled unit, looking at it from the outside. Not showing the electrical connections. This is only really the mechanical part of the assembly. So, if you have any questions, then feel free to ask, please.
Somebody must have some questions.
Will the outer pipe be opaque?
Yeah, I would opaque. It's a lot cheaper just to use regular PVC Schedule 40 pipe. It's tempting to get clear pipe, but at that size, and unless someone has some laying around, it costs like about $40 for 2 feet of the 4-inch acrylic pipe.
Yeah, actually, it might be possible to heat bend some polycarbonate from the hardware store, which would probably cost $20 or $30 for like a sheet of polycarbonate.
Uh-huh.
So that'd be like bulletproof glass.
Right, that would be nice. A good strong material, that's for sure. It means you end up with a seam, and you have to have a mandrel. You know, you can bend it around a 4-inch mandrel or something. Then.
Yeah, well, I can do the bending with the heat gun. I just need. There's going to be a seam. I'm not going to grind the seam out.
Uh-huh.
Not happening.
You could use the same interlocking pattern you use for your laser cut wood.
No. Just getting the curve to come to a complete pipe that's reasonably round will be difficult enough. It's not going to be as pretty as a PVC pipe, but it will be transparent. The problem is that you can get acrylic tubes that size. They don't sell polycarbonate round like that, and the acrylic's going to be brittle. So if you really want this as a safety guard, then you want either the PVC or polycarbonate. So a clear acrylic would just shatter.
Yeah. Yeah, as the PVC, it's even available in Schedule 80. You know, thicker sizes too. If we want a little more meat there to guard against things flying apart.
No, I'm thinking just a 1/4-inch sheet of it from Tap Plastic or the hardware store or something.
Oh, the polycarbonate, yeah, that's like Lexan or something, really thick stuff.
Essentially the same thing, yeah.
Has any part of this been built, or is it still just design phase?
Design phase.
How long do you think it would take to fabricate it?
Fabricating, normally probably I'd have estimated around a month to get the parts once the laser cut and delivered under today's conditions.
Well, and so
how
when
do you feel, John? Do you think that's doable? I'm basically, if I were to order, if we order it from Pinoco or another commercial place, probably looking at a month. Then John, if he gets access to some machine.
Yeah, I'm looking at purchasing a CNC and a laser cutter and a 3D printer right now.
Where are you going to keep it?
At the house here in San Jose.
Wow.
I've got plenty of room here.
Okay.
So what do you expect to see when you run this? What kind of, how do you expect it to perform?
My belief is that it should lift off. But if it's not strong enough, we should see weight loss on objects above the device. or weight gain. If we have the knife feel in the wrong direction, you'll see the objects get heavier. If you have it in the right direction, you'll see objects get lighter.
I'll be really amazed if it works, but it's such a huge game changer. It's worth the long shot. It's like, yeah, you know, it's a pretty low cost experiment to run. I don't expect this to cost more than a couple $100 for everything. So, yeah, I mean, this would be a real game changer though if this theory pans out and, you know, we get any weight loss at all or gravity modification effects. But that's because Ben has seen it in his previous experiments. He's actually seen the effect. If I actually see this, then yeah, it would be pretty amazing. But to me, the best thing to do is just build it and see and test it, see if it works. The idea, the way this is designed too, is that we can change parameters that verify the curves, so that the distance between the plates can be varied by using different pipes. We adjust the voltage for several different levels, and we try out different magnet setups, different magnet arrays. So,
and speeds.
And yeah, and also, you know, with a motor controller, do different speeds. So we just generate a set of curves and see what results we get, test them to see if they confirm Ben's theoretical analysis.
Well, you know, if we get any kind of number that's beyond nothing unusual, then you know, then we're not getting anywhere. But if we get any small anything, we can start very quickly, I think, optimizing.
Exactly. Yeah. I do think there's a number of things we could optimize for, I'm sure.
Do you have a suspension system in mind to suspend it and then run it that way, or do you have a some sort of weighing machine to be able to test, you know, lightness or heaviness?
It's a 5-inch square, so it can fit on a scale. So we can just measure the, you know, the weight that way. Or put sensors under the feet, pressure sensors.
Yep.
Measure change in weight. Do you have any thoughts on that, John?
Yeah, there's a chip called the HX711, which I've used for digital scales. So I can rip apart a postal scale or any kind of bathroom scale, wire it into that chip, and do like really long sample rates to get very high precision measurements. So we did a couple projects at the dojo with this, including a sort of hoverboard simulator. So yeah, modifying that. I think somewhere I had the Wiimote platform, the Wii scale platform somewhere. If I can get that back from the dojo, I could just hack that.
Did you say the whole thing? It was only going to be about 5 inches in diameter, or 5 inches wide.
Yeah, the outer diameter of the pipes is 4.5 inches, and yeah, the FRP boards are 5 inches square. So as you can see, like the feet themselves sit on about a 4-inch square, or 4-inch diameter scale.
I suppose you could just put a scale under each leg, and then just see if there's a change when you turn it on.
Yeah, well, that's the idea. The whole thing can go on a precision scale. I've got friends I can borrow, worst case, or we can put, some sort of sensors under each foot. I don't know. Last time I did something like this, we had, it wasn't for this, it was for precision measuring stuff, but Yeah, I just went down to like a thrift shop and ripped apart a cheap scale from the thrift store.
Of course, don't forget a tether just in case it decides to fly away.
Oh, you know, I told him the secret to anti-gravity is the right fishing line. But you know, I'm really good at building stuff. It's a drone motor, a couple of circuit boards, you know, and we can adjust the parameters. I'm not expecting to see much. I would love to be disappointed.
Yeah, by default, the motor will be tethered and the electrified plate or plates will be tethered.
Well, there's going to be definitely a bunch of wires for sure. Yes.
Do you have the requisite power supply for the high voltage?
I was going to try and pick it up. I left it at the dojo, and things have been closed since the COVID thing. So tomorrow, I think I'm going to schedule an appointment. Oh, that reminds me, I should send the message before it gets too late.
Yep. Make a list of all the parts you might need to look for.
Well, it's just the power supply there I'm going to grab and leave the rest.
You were looking for the scale.
I want to try and get as well. Oh,
Yeah,
the scale.
there's more than just one thing.
Yeah, well, we might want to.
Any other scrap materials from the laser lab and stuff like that?
Not really.
Now these mills, would you be able to mill like 1/8" FRP with the CNC you're looking at?
John?
I cannot hear you.
Maybe he dropped off.
No, he's still present. His mic is on. His
Yeah.
video is.
And another thing I wanted to mention is the hardware on this is stainless steel screws, stainless steel washers, and brass nuts. That's to make it all non-magnetic, so that there's no magnetic materials in here other than magnets themselves.
Yeah, I was going to ask about that, but I figured you.
Yeah. And the brass nuts.
Keep in mind, we should either order this stuff on like DigiKey or someplace, or try and get it from a hardware store first, because I don't think, you know, a lot of these hardware stores are fully open.
You can
And
also
certainly
get I'm sorry.
No, go on.
I was going to say you can also get Delrin rods and threaded rods, can't you?
Yeah, no, Delrin's, they do sell them as screws. They're quite a bit more expensive.
Yeah, the original.
You know, it's all special order. They have nylon as well. That's probably about quite a bit cheaper.
Are you planning to have any build days for other people to maybe bring some parts or help piece stuff together, or work separately? And
the only part I'm a little gray on is the rubber feet on the bottom, but this thing should build pretty quickly. I kind of like the idea of having metal screws to kind of cage in stuff if we do like a 10,000 plus RPM test. You know, one of these little magnets will be a projectile.
Yeah, in fact, the original design was fiberglass threaded rods. That was mostly for electrical conductivity and 3/8 inch. By the way, about everything I have in here is sourced from McMaster-Carr.
Okay.
So it's all available off the shelf. It might be cheaper on Amazon or local sources so that you don't have to buy large packs, because a lot of the stuff, some of the hardware comes in packs of 50 or 100.
Yeah, MasterCard's pretty expensive sometimes. DigiKey's not really all that cheap either, but you can order, one if you wanted to.
Well, Home Depot was also open.
That's my first preference. If, beggars can't be choosers, and yeah, brass or any kind of non-ferrous metal, it's, I think it'll be good.
I used to use, well, when I lived in Florida, there's a place called Small Parts in Miami, and they just have everything. This type of thing, anything you'd be looking for, I think. And they have a catalog. I haven't looked in a long time, but it's called Small Parts in Miami.
Okay, let me Google that.
Yeah, Small Parts was actually bought out by Amazon.
Really? I don't know what Amazon would want with it.
I think they might have discontinued it. So yeah, it's unfortunate.
Smallparts.com points to Amazon. A website says here. This is like 2012. They got bought by Amazon.
Yeah, there's still Berg and Stock Drive Products. It has like small hardware. Yeah, Small Parts though is nice for a lot of these other kind of small hardware items.
Well, there's Excess Solutions down here, which has a massive inventory of just random screws and bolts and whatever surplus, but it's really hit or miss on that place.
What's it called?
Excess Solutions.
Oh, okay.
They're by downtown San Jose. What's that? Santa Clara Street and 10th or something like this. There's a stadium over there. Was it Center Drive?
That's called Excess Solutions.
Yeah, EXCESS Solutions. And then what I also found is there's an Ace hardware store over on King in San Jose that's got a really good selection of stainless steel and other parts. Way better than Home Depot. Especially on
not
a
hard,
lot of these
way better than
tiny metrics that I need.
Cool. Yeah, of all the places, Placerville had a really good hardware store that has all kinds of hardware. That it used to be Orchard was good, but they're not in business anymore. So yeah, maybe that's kind of typical of Ace Hardwares, that they have better hardware selection. Because that's the hardest part to find. Brass nuts are pretty common. Stainless steel washers, but 4.5 or 5 inch long screws are probably less common, be harder to find. So
yeah, just take apart your local street light.
I think that's a little bigger than 1/4 inch screws though. I see the design I have up here. This is with the 3/8 inch fiberglass rods. Yeah, this one's more expensive and nylon nuts and washers.
Anyway, changing out the screws are fairly easy. The whole point is this is a test bed that we can very quickly change between different settings and adjustments and thicknesses and heights.
Yeah. Yeah, that's what I figure. So.
Any other questions?
Not at the moment.
Hello?
Yes.
Can you hear me?
Yes.
Yes, I'm just wondering what kind of voltages you're using between your plates. like 40,000 kilovolts or less or more to get the effect
modeling
you desire?
suggests anything above 1,000 should work. So it's up to what the materials can handle.
I have a power supply that I can adjust. I don't know what the low end is, but it was adjustable up to 20,000 volts that I left over at the dojo for this project. So, you know, when I get it back, I'll be able to look at the settings again. A friend of mine was throwing it away, and I was like, "Ooh, let me grab that!" Like 2 years ago, and then this project came up. So it's like, yep.
What's the difference, or what's the distance between the two plates to prevent dielectric discharge?
Mike Doty set that, but it's adjustable.
Oh, good.
1 inch. Current design.
Yeah, generally the voltage won't be that high where it would jump.
And we could always throw, you know, some sheets of glass or acrylic or something between them if we had to. You know, does the dielectric in between make a difference?
Like, that was kind of the main consideration to having the fiberglass rods originally, was to.
No, I mean between the two plates.
Yeah, right. But within we can just insulate all but one of these connectors on opposite corners to maintain enough separation, you know, to run a few thousand volts on this.
And the other device in the video wasn't only one plate electrified, not two?
Well, one's ground and the other one's going to be your voltage. So it's a DC. We're just looking at DC on this.
Okay.
So, are you thinking of this diagram here? This one is showing it's like you're using a common ground on your motor and bottom plate, and then you have your positive high voltage on this top plate.
Yeah.
But then it gets messy, you know, as far as you're isolating your motor electronics from high volt, from the any, you know, ground noise. Use this ground, and you got to, you're also getting connecting that electric. You need like a slip ring of some kind. So this is here to have another plate, a bottom stationary plate.
Well, hopefully it still works with them being that removed.
Yeah, because kind of originally we were using that Russian design, and we're kind of skeptical though of that, what he was doing. So that's why I just kind of went based purely on Ben's design and the original Russian design that used the super cooled discs, and not the other one that had the videos that looked suspiciously like they were on strings or something. So.
Lorentz design.
With clip move, yeah. He also had some other exotic bismuth type discs, I think.
Yeah. But I estimate, I did the calculations, reverse the calculations. He's spinning at 8,000 to 13,000 RPM, which means his disc is probably about 2 centimeters in diameter. So this, you don't have to spin it as high as that, because it's a much bigger disc.
Yeah, so we've gone down from this. This is like about a 10-inch diameter disc. And now we're down to a 4-inch diameter disc. So we can use it makes it a lot easier on the motors and the strength and everything. lowers a lot of costs. Those got to be probably $400 or $500 for the original design. Now we're in the $100 to $200 range, so, and a lot easier to make.
Yeah, you can spin up the one disc a lot more without having to spin the top disc in the opposite direction.
Right. And it gets into interesting questions, like based on the Faraday paradox, is with a homopolar generator, is if you have a north-south field and you spin a disk in it, a conductive disk, you get a current in voltage from the center to the outside edge of the disk. And also, if you spin the magnet along with the disk, it still produces that voltage, that current. And only the magnet and hold the disk stationary, then you don't get any current.
I have a suggestion. To build a large enough ferrocell that you can use to inspect the device while it's static and while it's running for the different magnetic fields and the interactions.
What kind of cell?
Ferrocell. You know what that is?
No.
No, I'm not familiar with it.
Okay, so a ferrocell is a way to visualize magnetic fields simply with glass, ferrofluid sandwiched between two pieces of glass, hopefully nice clear optical glass, and illumination on the edges of the glass. So let's say the glass pieces are round. You have a round disc of glass on the bottom. You have this ferrofluid, which is essentially, you could use your blood. Your blood is a ferrofluid because it has ferrous material inside, right? So a half a drop of blood on the plate, then sandwiched with another glass plate on top. It spreads out into a very, very, very thin sheath. And then that sandwiched together, you can usually build a kind of a black dark housing that encompasses maybe an LED rope light kind of a thing, or an LED strip that's going to be illuminating towards the center, and that shows you some really beautiful magnetic field effects when you bring a magnet into the area of the plate. Yep, and so those are the images of what it looks like.
Huh.
Very interesting.
So it's pretty simple to build. Yep. You can look up some designs. Last time I looked, there was many people building them overly large, overly complex, but really you just need 2 plates and some ferrofluid. I'm gonna have to step off. Phone call and dinner's planned, so thank you all for the presentation. I'll catch you another time.
Yep. Thank you, Rob, for joining.
Got it. Bye-bye.
Bye. Yeah, these are a lot better than the film you can buy at K&M Magnetics. That's
Yeah.
This it could see
What's
the
happening?
field line spin when you spin the magnets.
Yeah. Any other questions?
Nope.
Okay. So shall we end this?
Okay.
Okay. Mike, can you get out of screen share so I can put up the last slide, and then I'll end the recording. Okay, great. Okay, so the last place was basically how to reach the gravity modification group. I'm going to post this on the web so everybody can have a look. And so you guys have a great time. I'll figure out a next topic and the next session. Thank you so much, guys.
I've got a piece of that magnetic material if you want to see a quick demo.
Oh, yeah.
This is a fridge magnet. This one's been in my box for like 20 years, so it's a little beat up, but you can see the magnetic field underneath. It's just a fridge magnet.
Wait, just a minute. I lost my video somewhere.
Okay.
Oh, right.
So there's the magnet, and there's the paper over it, seeing the magnetic field. It's not very sensitive.
Yeah.
But this is a, you know, like when it first came out, sample that I grabbed. So.
Yeah, that's a possibility. That's something we can incorporate.
Yeah, I think that the field pattern on this is going to be pretty well understood. I don't think, you know, unless you're just trying to do, you know, impress people.
Yeah.
Okay.
Okay, folks. Have a great time, and I will schedule another meeting soon. Thank you.
All right. Bye.
Thank you.